All right, in this video lesson, we're going to be talking about what is called linear programming. In this video, we're going to talk about kind of the basic parts of linear programming, and then in a follow-up video, we'll actually work through two entire linear programming problems all together. So these are kind of the basic pieces that you'll need in order to solve those problems in the next video. So let's start by talking about what linear programming is. So linear programming is where you use a system of linear inequalities, which inequalities similar to equations, a little bit different, in order to maximize or minimize an objective function. Now, if we're going to do that, here's kind of our steps to linear programming. Step number one, which we're going to do today, is we're going to graph the system of inequalities, which are known as the constraints. We're then going to find all the vertices which define our feasible region. And then in 3, we're going to find the point that's in our feasible region that either minimizes or maximizes the objective function. Now this next principle is a very important one. It's called the vertex principle of linear programming. And you don't need to remember what it's called or what it says really, just what it does and what it allows you to do. It basically says that if there's going to be a maximum or a minimum value of the objective function, then it has to occur at one of the vertices, or if you want to think about the vertices as being the corners of the feasible region. That means because our feasible region is going to be kind of a section of the graph, and to try to check every single point in that section, not only is it hard, but it's impossible because there's going to be an infinite number of points in that region. So the good news is this principle basically says you don't have to check all those points. You just have to check the points that are on the corners or the vertices of that particular region. So let's take a look at a couple examples of kind of how this works. So for number one, we've got a system of constraints. We've got 3 inequalities that we're going to graph, which are that y is less than or equal to -1/2 x plus 3, and then that x is greater than or equal to 2, and that y is greater than or equal to -1. Let's start with our first inequality, which is that y is less than or equal to -1/2 x plus 3, which I'm going to do in red. So in order to graph that inequality, we're going to graph it at first similar to how we would graph a line or an equation. So we're going to start at +3 with a point there, and then we'll use our slope, which is -1/2, to place a few more points on our graph. So -1/2, and here we go. Now, a couple things to worry about for inequalities. The first is what type of line you're going to use. If you have a less than sign or a greater than sign, you're going to have to use a dashed line to graph your inequality. If it's less than or equal to or greater than or equal to, instead, you're going to use kind of a normal line. So you're going to draw in a line like you would as if you were graphing an equation. And so for this particular example, because its y is less than or equal to, that's going to be what allows us to actually draw a filled in line through those points. The second part about inequalities is how you are to shade. So if you have a less than or equal to sign, that's going to be your clue to shade below whatever line you drew. If you had instead a greater than or equal to sign, you're then going to shade everywhere above that line that you drew. So in this case, because it was y is less than or equal to, that's our clue that we're going to shade basically everything below our line that we just drew. So that would be kind of everything right below here, which I'll shade in for us, is everything right in here. All right, so that's our first inequality that we're going to use. Our second inequality is where x is greater than or equal to 2. Because it's x and think about it as being x equals 2, that's your clue that this is actually going to be a vertical line through x equals 2. Because it's greater than or equal to, we're going to use a solid line. Now, notice that for this particular inequality, there is no above and below. So while you're thinking greater than or equal to would be above, there is no above this line. So instead we have to think about, is it going to be to the left or to the right? And if we want for x to be greater than or equal to 2, that's our clue that this is going to be everything to the right of that line that we drew. So you can see where, as I'm shading, there's now kind of this region in the bottom right of the graph that's been shaded over twice. So far, that's going to be our feasible region. And then depending on this last inequality, we're then going to finish our feasible region. So it tells us that y is greater than or equal to -1. So similar to how you graphed x being greater than or equal to 2, for y you're going to do the same thing. The only difference being that this is going to be a horizontal line. And now you actually can think about graphing either above or below. In this case, y is greater than or equal to, that's your clue that this is everything above that line that we just drew. And now you should have seen that there was one region that got shaded in 3 different times. So it's usually going to be the darkest region that you can find on your graph. In this case, that feasible region ends up being this little kind of triangle right here. So there's our feasible region. We should also identify the vertices, or what points are on the corners of that feasible region, and there's 3 of them. The first is at 2, -1. The second is at 2, 2. The last is at 8, -1. So what we're going to do is we're going to figure out which one of those points will give us a minimum for this objective function, which it already has in this table set up for us. We're just going to use those points that we just found to figure out which is going to give us a minimum. So as we plug those in, we'll use both the x and the y value. So we would take 3 multiplied by 2 plus 4 multiplied by -1, which becomes 6 minus 4, which is 2. For the next one, we'll take 3 multiplied by 2 plus 4 multiplied by 2, which becomes 6 plus 8 is 14. Lastly, we'll take 3 multiplied by 8 plus 4 multiplied by -1. That becomes 24 minus 4 is 20. We were looking for the minimum, and so for the minimum, that would be this first one right here where the c value is only 2. So our point of 2, -1 would be our solution for this particular system of inequalities. Let's take a look at one more example of this. So in this next example, for number 2, for our first 2 inequalities, rather than shade them in, let's just think about what that means. So when it says x is greater than or equal to 0 and y is greater than or equal to 0, well, x is greater than or equal to 0 would be everything to the right of the y-axis. Y is greater than or equal to 0 would be everything above the x-axis. So really what that says is, if you can see, we're going to be focused on this top right quadrant. So we're going to be focused on the first quadrant of our graph. So I'm not even going to graph the x and y greater than or equal to 0. All I'm going to do is make sure that we are only looking at kind of this top region. So I will put in some lines there just to remind us that we are only looking at this first quadrant of our graph. As for our other 2 inequalities, let's go ahead and take a look at those. So the first is that y is greater than or equal to 2x minus 4. So we'll start that at -4, which would be right here. And then 2 is our slope, so up 2 and over 1. And we can continue to do that. And then we can draw our line through those points. Now again, for shading, we are greater than or equal to in this case. So let's go ahead and shade everything above that line. Remember though that you're staying in the first quadrant, so that would be basically everything right here. Next, for y is less than or equal to -x plus 5, let's graph it. So that would be starting at +5. Our slope is -1, so we're going down 1 and over 1. And we'll continue to do that through those points. So here would be our second line. Let me get that moved around a little bit to make it go through. There we go. Cool. And this time, y is less than or equal to tells us we're going to shade everything below that line. Again, remember that you're staying in that first quadrant. So now the feasible region should be pretty clear. There was only one place that you shaded twice, which is this little piece right here. Now, for that piece of our graph, for that kind of polygon shape, we're then going to have 4 vertices that we are going to use. The first is at the origin, so 0, 0. The next is at 2, 0. We also have one at 0, 5. And lastly, we have one at 3, 2. All right. So then filling in our table, notice that this time it hasn't been set up for us. So just as a reminder, the way you'll set it up, your points will go in the first column. Your objective function, which was right here, will go in the center. So x plus 3y was our equation that we're using. And then p is what we're looking to, in this case, maximize. So remember, for number 1, we were looking for the minimum. Now we're looking for the maximum. So for our points, we've got 0, 0, 2, 0, 0, 5, and 3, 2. Plugging those in, probably not going to get a maximum at 0, 0 because their p is just 0. At 2, 0, we're going to have 2 multiplied by 3 plus 0, and that's just 2. At 0, 5, we've got 0 plus 3 multiplied by 5, and that is 15. So far that's our maximum. Let's check our last one here. 3 plus 3 multiplied by 2, and 3 plus 6 is 9. So it does look like our point at 0, 5 is going to give us our maximum for p. So that's kind of the math behind what we're doing in linear programming, is we're taking this system of inequalities and graphing it and trying to find which one will maximize or minimize some objective function. We need to put this in context, though, because without the context, this is just another math problem. So let's take a look at kind of how we'll set up our system of inequalities from a real-world scenario that we might come across. So in this scenario, we have a farmer who has 10 acres to plant in wheat and rye. He has to plant at least 7 acres. However, he only has $1,200 to spend, and each acre of wheat costs $200 to plant, whereas each acre of rye costs $100 to plant. So some key information so far: we've got 10 acres, we need to plant at least 7, we've got $1,200 to spend, and it costs $200 and $100 for wheat and rye, respectively. Moreover, the farmer has to get the planting done in 12 hours. It takes an hour to plant an acre of wheat, 2 hours to plant an acre of rye. If our profit is going to be $500 for each acre of wheat and $300 for each acre of rye, how many of each should be planted to maximize the profits? So that's kind of our goal, is going to be to maximize profits. Now, to try to just come up with that all at once is hard, so we're going to break it down into some smaller steps. Let's first figure out what variables or unknowns are involved. So there's actually 2 different variables, because we want to know how many acres of each should be planted. So let's let W be the number of acres of wheat, and let's let R be our number of acres of rye. And we're wanting to know, what is W going to be equal to and what is R going to be equal to. Next, what is our constraints? So what constraints do we have? What are we limited by is basically what we want to be thinking about. Well, we're limited on space. If you think about it, he only has a total of 10 acres to plant, so we don't have all the space in the world. We're also limited by time. If you think about it, he only had 12 hours to get the planting done. Lastly, we were limited by money. He only had $1,200 to spend on his acres of wheat and rye. For the third part, what quantity are we going to maximize or minimize? Well, we're wanting to maximize, in this case, profit. So profit is what we want to maximize or minimize, and in this case, pretty clearly you want that to be maximized. So let's go ahead and start writing out some of these equations. So a farmer has 10 acres to plant in wheat and rye. To find the variables, those are same as above. So we've already defined those in number 1, so I'm not going to worry about copying those down. But for number 1 up there, you've got W is acres of wheat, R is acres of rye. Now, he has to plant at least 7 acres, which means that if you take your number of acres of wheat plus your number of acres of rye, then that has to be at least 7, so greater than or equal to 7. However, he only has $1,200 to spend, and each acre of wheat costs $200, whereas each acre of rye costs $100. So, to write another inequality, we could say that 200 for each acre of wheat, so 200W, plus 100 for each acre of rye, so 100R, can only be as much as 1,200, so has to be less than or equal to 1,200. Then if you wanted to simplify, because a lot of times simplifying makes it easier to graph, notice that you can divide everything by 100, so you could have also said that 2W plus 1R must be less than or equal to 12, which does make it a little bit easier to graph. Moreover, the farmer has to get the planting done in exactly 12 hours, or in 12 hours or less, and it takes 1 hour to plant each acre of wheat and 2 hours to plant each acre of rye. So 1 hour for each wheat would be 1W, plus 2 hours for each rye, so 2R, must be no more than 12 hours, so less than or equal to 12. And in this case, it looks like it's already as simplified as we can make it. Now, here's a very important one. There's actually 2 more constraints that we have, which is that you cannot plant negative acres of wheat and you cannot plant negative acres of rye. So if you cannot have negative, then that means the number of acres of wheat must be at least 0. And that the number of acres of rye must also be at least 0. We call these the non-negative constraints, and they're ones that are easy to forget. So make sure that as you're working through problems on the homework, and even on the project that we'll be talking more about for class, that you are always including those non-negative constraints. Lastly, to set this one up, if the profit is $500 for each acre of wheat and $300 for each acre of rye, how many acres of each should be planted to maximize the profits? We're going to write our objective function, so we'll just call it P for profits, which is that we're going to get 500 for each acre of wheat and 300 for each acre of rye. So that would be our equation that we would use. So thinking about kind of where this is headed, we would then do what we actually worked on for numbers 1 and 2 on the previous side of the notes, which is that we would graph these 3 inequalities right here. Obviously, these just tell us that we are in the first quadrant, so we really don't need to graph those as long as we remember that. But once we graph those 3 inequalities, we would then set up our table. We would use our objective function in the center of that table, so something like this. And then we would go ahead and solve to see which one would maximize profit. Now, we're not going to do that for this problem. However, in the next video, we do have 2 different problems that we're going to work through in a similar way where we will actually get all the way to our solution. Until then, have a good rest of your day.